Welcome to my talk. Thank you for attending. This talk will be a little different from the majority of the other talks that you've heard over the past 2 days, because I'm not going to be talking about features of C++ directly, but about a framework that is powered and enabled by C++, and I will try to touch where exactly C++ helps us to implement the things that we do. So a little bit about me. My name is Avi Kivity. In my previous iteration, I was the author of the KVM hypervisor, which is now running most of the clouds. That was mostly a C project, both the Linux kernel and the QEMU. And now I'm the CTO and the co-founder of ScyllaDB. We're building a high-performance open-source NoSQL database. My details, my Twitter handle is there if you're interested in snide remarks and sarcastic comments. And my email is over there. It's not because I'm a relative of Steve Jobs, although maybe it would be better if I were, but because we are hiring, and that is not only for locals. We are very remote friendly. So if you like what you see in the stock, please drop me a line. All right, and with that out of the way, let's talk about Seastar. So Seastar is a framework for asynchronous programming, multi-core disk I/O and networking, written in C++, and that heavily leverages C++. So we require at the minimum C++ 14, and also work with C++ 17, and even use some features from C++ 20. So let's start with a little quiz. Does anyone recognize the picture? What's in the picture? All right, so that was an obvious trick question, and it is an SSD, but the aspect of it that we are interested in is that it acts as a network device. So so over here there is a connector that is a networking port. And the way that the machine interacts with the SSD is by sending it commands for read and write, and then waiting until the command responds. And that can take around 100 microseconds on these kind of SSDs, and maybe 20 microseconds on the modern NVMe devices. But from the computer's perspective, it's an age. So in 20 microseconds, the CPU can execute 20,000 instructions. But we don't program it in this way. We program it using read and write APIs that are mostly synchronous. So you issue a read, and then the threads that cause it blocks. And that means that a lot of things have to happen under the covers. The thread has to be switched out and then switched back in, and that is all very expensive. And nobody would dream of doing the same thing on an ordinary network device. You wouldn't use blocking calls. Everything in networking is done asynchronously. But here, even though this is really a network device, everyone programs it synchronously, and that's not very good. All right, next question. Does anyone recognize this thing in the image? And now there's even a helpful label that describes it. So anyone cares to take a guess what this is? Okay, so it didn't help that I said that I'm only doing trick questions. So this is also a network device, all right? It is a Xeon processor, and those little squares in here, those are all cores. But the reddish brown thing around, this is really a network that is connecting all of the cores, and there are 2 such rings, and they're bidirectional. So when one core wants to talk to another core, it sends a message on the network, and it travels across the ring until it hits this switch, and then it traverses over to the other ring, and then travels around that ring and hits another core, and they're communicating. And there are also, if you put 2 of those together, then the 2 processors will communicate over an external network. So even though it is the CPU that powers everything, it actually has a lot of networking components. But again, we don't program it as if it were a networking device. Everything is done synchronously. So when we want to communicate between cores, that is sharing data, what we usually do is take a lock, access the data we want to access, and then release the lock. And all of these operations are translated to messages on the network, but we simply ignore them. And again, this is bad because, well, at a small scale, it's not so bad. But when you go to large scales, all of those locks translate to messages across this internal network, and those messages take time to propagate. And we refer to that as cache line contention. And also, when you take a lock and you don't succeed, you need to wait. And again, this dance has to happen where the kernel puts the thread that is trying to take the lock to sleep, tries to schedule another thread in its place, and then has to wake it up when the lock is released. So it takes a lot of work and a lot of network messages to make this network machine behave like a serial machine. And what Seastar tries to do is to treat disks and multi-core in the same way that we treat networking, that is asynchronously. So what I said before about multi-core becomes even harder when you have multiple processors, because each of them also has its own memory, and that is called non-uniform memory architecture. And when you have one core from one socket trying to communicate with memories that are attached to another socket, then that can take up to 400 cycles to get that memory, and that is, again, ages in terms of processing time. So you could execute, by the time that you get the response back, you could have executed hundreds of instructions, perhaps even 1,000. So this is the results of a Seastar HTTP server running on a large multi-core. And what you can see is that the scalability is linear. The horizontal axis is the number of cores. And you can see comparisons to, this is actually memcached, not HTTP. And you can see that comparisons to stock memcached and the performance is both higher per core, and also the scalability is much better. So with Seastar, you can write an application in a way that takes advantage of today's large multi-cores. And 20 cores is actually not a lot these days. You have machines that have 64 cores and even more. This is a comparison of a database implemented on top of Seastar, which is the product that my company is working on, compared to a database that uses the same APIs, that does not use Seastar and does not use the techniques that is used by Seastar. The comparison is versus Cassandra. And you can see that we're comparing here different numbers of nodes. So on the left, we have 3 Cassandra nodes in red. And you can see that the number of operations per second is around 100,000, 120,000, and the latency is quite high. And when you go to 9 nodes and 15 nodes, the throughput increases and the latency is quite high. But if you compare that to a 3-node Scala cluster, the operation rate is much higher and the latency is much lower. So this is what can be achieved by careful attention to the fact that that processors and disks are really network devices and not the synchronous devices that we usually treat them, the way we usually treat them. So this is another way to look at threading in traditional applications. So in a traditional application, you have a bunch of threads, and those threads are multiplexed onto a number of cores that the machine has. And you have a sort of dilemma. So if you have a very large number of threads, then the kernel has to switch in and out those threads so that each of them will get a CPU time on a core. And this switching is both expensive because you have to put a thread to sleep and then wake it, and also it induces latency because the thread will have to wait for its turn. On the other hand, if you put a too low number of threads, then you will have cores that don't have a thread to execute, and the machine will be idle. And it is common to see that on a large machine, you run an application, and it's only consuming 30% CPU or 40% CPU, and you try to load it more and more, and it's not going to consume CPU. It's very hard to find where the bottleneck is. So the Seastar model is to have 1 thread per core so that you have the exact balance. You never have a situation where a core doesn't have a thread to run because there's an exact match between the numbers, and you never have a situation where the core has to multiplex multiple threads, because again, there's exactly one thread. So we solve the problem of assigning threads to cores, but of course we gain the number of problems about how those threads can do different tasks that we usually assign to different threads. So this is, again, the same thing with, in a different way with more details. So you have a bunch of threads, and you have the kernel being responsible for assigning them to cores. So in Seastar, the model is different. Instead of having this pool of threads and pool of cores, and again, a pool of resources, it's not just threads and cores, it's also memory and connections to the networking card. Instead, we partition the machine into a bunch of replicas, which are called shards, and each of them runs the same code in parallel. And because of that, the amount of communication between the shards is minimized. So each of them is sort of standalone. They have means to communicate with each other. So each core has a point-to-point queue. So every pair of cores is connected by a queue, and all of the intra-core communication is done via these queues. There is a scheduler, a task scheduler, and the role of the task scheduler is to give us back the abilities that we lost when we enforced the one thread per core. So instead of having a large number of threads, each of which perform a single task or a single process, all of the work is multiplexed, and the way we control that is via a task scheduler that picks the next task to execute. And this is basically a class with a single virtual function. There is a queue of these tasks, and the scheduler just picks the next one to run and execute it. So it's a simple run-to-completion scheduler. We also have a user space TCP/IP stack, but in the interest of time, I'll skip over that. So that's, that describes the user space networking stack, but again, maybe we can go back to that if we have time at the end. So to summarize, in Seastar, so each logical core, that is a hyperthread if you run an Intel or modern AMD CPU, it runs a shared nothing run-to-completion task scheduler. So it's basically a first in, first out queue. There is a little bit of extra logic in that we also allow prioritizing different tasks to run at different times. The different cores are connected by queues. So all of the communication is explicit. Each core, each thread owns a piece of the system memory. And when it wants to communicate with, if it wants to access data that is owned by a different core, instead of taking a lock in order to exclude those other threads, instead it sends a message to those other cores and asks them to perform an operation on its behalf. And this way, the remote node, the remote core does not need any locking. There's only one thread accessing each piece of data, and all of the costly locking instructions are avoided, and also locking becomes much simpler because everything is serialized by the remote core, and we avoid all of the internal networking operations that the CPU has to perform under the covers in order to move the data to the core that executes the operations. So instead of moving the data, we move the operation. So the nice thing about the Seastar APIs is that they're all composable. When you have a networking operation and a disk operation and remote core operations, you can combine them in different ways. And that is enabled by the API, which we will talk soon. Usually, if you have an asynchronous networking stack, but a synchronous, synchronous disk access and synchronous memory access based on locks, they don't combine well. As soon as you take a lock, you have to complete everything and then release it. Otherwise, you're going to cause other threads to contend. So you cannot, if you take a lock and then perform a disk operation, you will hit contention. And Seastar solves that by making everything asynchronous. So the building block in Seastar is a future promise and continuation model. How many people are familiar with futures? So almost everyone, that's great. So that was invented way back in the 70s and recently came back into fashion with Node.js using it, and also C++ has, in the standard library, has the futures and promises. So it's a very good way to compose different activities. So what's a future? It's a result of some computation, and in Seastar, it's not just, it's even more than a computation, it's a result of I/O. So when we read from the network, we get the result as a future. If we have something that needs to execute sometime in the future, so we can ask for a timer that returns a future that will become ready when the timer expires. And the same with disk and multi-core. So when you issue a write to the disk, you get back a future immediately. And the future resolves when the write completes, and the contents of your future is the success or failure of the disk write. And the same with the computation on another core. So if you want another core to perform some computation on your behalf, because it owns the data that you're interested in, then you call an API that runs your function on that remote core, and that API gives you back a future that becomes ready when the computation is complete and will contain the result. Yes? So the future itself does not contain anything about inter-process communication. It's just a building block, but what happens under the scene is that we have a core-to-core queue, so a point-to-point queue, and when you ask a remote core to do things on your behalf, you write something into the queue. The remote core will read from that queue. Every half a millisecond, it pulls the queues, executes a function on your behalf, and then write a response on a return queue. And then your original core will pick up the result, find the future that is associated with that result, move the result over into that future, and activate any continuation that is attached to the future. And the nice thing here again that it is composable. So a future can not just be a result of one of those basic primitives, but it can also be a combination. And if you think about things like a distributed database or a distributed file system, you get some kind of request, and you want to replicate it into different nodes. So you have a future representing the result of each replication, and you want to perform a disk read or a disk write in order to put the data to disk. So you can very easily have futures that represent the completion of multiple events. So that's a future. It represents a result. A promise is the other side. A promise is something that delivers the result into a future. One way to look at it, if you're a low-level guy like me, that a future and a promise are really a queue that can hold at most one item. And it's a single use only. So you write something into the producer end of the queue, that is the promise, and it will appear at the consumer end of the queue, which is the future, and then they both disappear, maybe like an electron and positron that collide and disappear and release a lot of energy. And a continuation is a glue that connects all of these together. So when you have a future, you need to do something with it. So the something is a continuation that you can tell. It's a piece of code, usually it is a lambda, that tells the scheduler when that future becomes ready, here is what you do with it. You run this continuation, and the continuation accepts the future value as an input, and what it usually does is it gets converted into another future. So usually it will launch another I/O operation, and what we have is a bunch of I/O operations, which can be either cross-core calls, they can be disk writes or disk reads, or they can be networking calls, the continuations glue these together. So this is an I/O machine. We keep launching I/O operations, performing some kind of transformation on the result, and launching the next I/O operation. So this is how it looks in practice. So we have, say we're doing a simple key value data store, and we have a function that is called get, that reads a value from the data store, and of course it returns a future. It has to return a future because we may not be able to fetch the data immediately. Maybe it's on disk, maybe it's on a different node, maybe it's on a different core, so we cannot call it and expect to have a value immediately. So we wrap the value in a future, and we know that eventually it will become ready. And similarly, we have a put operation that, again, it accepts a value as an input, and it returns a future that tells us when the operation is complete. So here we have a complex calculation, and we have a function f, and what it does is it reads the value from disk or wherever, and calling get returns immediately. It doesn't wait for the disk operation to complete. It just launches the various I/O operations that are needed, whatever they are, and it immediately returns a future. And what we do with that future is we attach a continuation to it with the then function. The then function accepts a lambda, and that lambda gets the value which we don't know yet. At the time that then is executed, the value is not known, but it will be known in the future. And then we perform a computation, and the complex computation here is addition. And then we write it to disk, and we then print something to standard output in order to tell us. And we return that value. So what we did here was compose two different operations, and we compose them in a sequential way. So that's the simplest way to compose two operations, run them one after the other, and pass the results of the first operation into the second operation. So, as most of you know, there is also a future in the standard library. What are the differences between the standard library's future and Seastar future? Why did we have to write our own? So, the Seastar future, first of all, is single-threaded. It doesn't have any locks. It doesn't have any atomic operations. And so it maximizes the fact that we already forced everything in Seastar to run in a thread per core model. So now we are exploiting that. And that makes the Seastar futures much faster than the standard futures. It has embedded state. So usually in the standard library future, it's not really mandated by the standard, but all of the implementations allocate space for the shared state between the future and the promise, whereas our future has embedded state. So it avoids this allocation, and of course, no locks. And the continuation does require allocation, but conditionally. So if the future happens to be ready at the time that the lambda is invoked, then we will run it immediately and not allocate it. But if it's not ready, which happens quite a lot of times, then we do have to allocate space for the lambda. It's a good observation. So not everything is rosy, and indeed the framework is very allocation intensive. We routinely see millions of allocations per second per core. Yes? So maybe I should repeat the questions for the video. So the question was whether we're doing the small buffer optimization. And in fact, I tried, but it's pretty hard because there's really no place to put it. So we're still searching for a way to do that. But the fact that our allocator is not thread safe means that the allocations are not as expensive as they usually are. So it's still something that we're looking to improve. Okay, so let's look at ways to combine continuations that are more complex than the simple serial combination. So you can do things concurrently simply by not waiting for the future. So here is the sleep API. It's an API provided by Seastar, and it's also a nice demonstration of STD chrono. And you can sleep for different periods of times, and all of those waits will happen in parallel, and they will complete out of order. So those sprints will happen in the orders that you expect. That is, 100 millisecond sleep will happen before the 200 millisecond sleep. And F will actually complete immediately. It will run in less than a microsecond, but it will schedule continuations to be executed when those timeouts expire. Yes? Yeah, so question was, what happens if futures expire or become, the term is become resolved or become ready at the same time? They will run one after the other in an unspecified order. So the scheduler has to serialize all of the operations because it is running on a single core. And one of them will run, and then the other will run. You can't tell which. If you want to serialize two continuations, then you have primitives that let you run one after the other. Yeah.
What's the difference between the library UV and other
Okay, so the question was comparison between our library and libuv. So it's mostly about the ability to compose things. libuv and the other low-level libraries force you to do things in, you have to lay out the operations manually. In Seastar, because we use a higher level model of futures and promises, and also later we will see coroutines, you can write code in what appears to be sequential, in a sequential way instead of a nest of callbacks, and it becomes readable. So even though the code that we saw before with get and put, it looks like it's written sequentially, but it's actually executed out of order. So it gives you a high-level API to those low-level primitives of executing things asynchronously. And under the covers, it also has support for Linux AIO. So it's not just network, which is the facilities provided by libuv, as far as I remember. We also do the multi-core thing and disk access. So we provide a composable API instead of addressing just network. So it's not a wrapper around EPOL. It's a wrapper around EPOL, AIO, and our core-to-core queues. Okay, so zero copy. Because we're such performance freaks, we try to avoid copying. So we have a temporary buffer, which is a sort of a string type, but it has some nuances in that you can control the way that it is shared and deleted. So a temporary buffer is a bunch of memory, but it has, and usually you only move it from place to place, but when you read from a Seastar socket, you actually get the memories that was used to receive the packet. So if you're using the user space TCP/IP stack. So you get access directly to the memory that was accessed by the network card, and then you can pass it on to your application. And you can share those temporary buffers. So if you have, for example, if a packet contains objects that need to be processed by different continuation chains, you can split the temporary buffer into two, give each piece to another, and the temporary buffer will end its lifetime, will release its memory back to the system when the last user stops using it. So we also have threads. So writing everything in terms of continuations is possible, but as you saw, it's also results in somewhat messy code. And there are sometimes jobs like long-running computations that need to process a large number of objects and only rarely do I/O, perhaps because they have large buffers, so you only want to flush your buffer once it completes. So some tasks are better served by threads. It's easier to maintain state, and it's sometimes there's the right tool for the job. So Seastar offers its own version of threads. Those are green threads, so they are cooperative. And internally, they just compose to core continuations, the same continuations that are used to implement future continuations. And because of that, they compose very well. It's very easy to have, we can use the same get and put operations in a thread. We just call the function, so if we have read that returns a future, we just call get. And what get will do, it will pause the thread in case that the future is not ready. And once the future becomes ready, the thread will be resumed and it can continue running. And that is very useful for some things. And it's very easy for a continuation to launch a thread and wait for it to complete, and also for a thread to launch continuations and wait for them to complete. So it all composes very well. It's similar to Boost Fiber internally. The difference is the way that it interacts with the scheduler. So it is integrated with the scheduler, and during the lifetime of a Seastar application, it will run a mix of continuations from regular continuations and from Seastar threads. Okay, I/O scheduling. So in a complex application, you usually have different tasks. So maybe a database is serving requests from different users that need different SLAs, or maybe it is doing an internal maintenance task. Maybe it's doing a backup in parallel with a serving. So there is a demand not to allow one of those tasks to dominate the other. It's very easy for an internal task like a backup to send a lot of I/O requests to the disk and also for the CPU and starve out the other users. And that is something that we want to avoid. So the way we do that is we start by measuring the way that the disk responds to requests. What we have here is a plot that shows both the throughput in terms of I/O operations per second and the latency of a modern disk. So you can see here that as you increase the concurrency, on the x-axis is the number of concurrent requests that the disk is serving. As you increase the concurrency, the throughput increases more or less linearly. So that's good. You're pushing more data, and Seastar makes it easy to push a lot of requests to the disk because it's very easy to generate concurrency. You're not tied by the number of threads that you have. But after you reach about 150 requests, then the throughput stops increasing. You've saturated the disk. You're pushing more requests, but they're just sent into some queue to wait until the disk becomes ready to serve them. What doesn't start increasing is the latency. So not only you're not getting better throughput, you're actually increasing the latency. So what Seastar does is it does I/O scheduling in user space. Instead of sending all of the I/O requests that we have directly to the disk, we block them in the scheduler, and we have our own queue. We allow as many requests as the disk will be able to exploit. So up to 150 in the case of this disk, and the rest will be stored in the Seastar scheduler. And what that gives us is that we can choose. We can have multiple queues. We don't have to send requests to the disk in the order that they are generated. We can pick a request from different queues. So for example, if we have a commit log queue and a compaction queue, let's not dwell on what those mean. We can, and they have lots of requests waiting. We can choose not to select a request from that queue. Instead, we can select a request from a different queue, let it pass all of the others. I think Israelis know the concept of passing queues quite well. And this way, we will provide, on one hand, we provide really good service to the queries, to the user queries, so the user is happy. But on the other hand, we also fully utilize the disk because we are not limiting the disk at some kind of arbitrary, we don't just throttle the disk arbitrarily, we feed it enough requests so that it is fully utilized. And this facility is exposed, of course, to applications, and this way applications can provide things like SLA to the user or balance internal processes. Yes? Okay, so the question was, how does the actual talking to the disk part happen? So we use the Linux AIO API, which is a less well-known part of Linux. And what it does is it forms a pair of queues between the application, between the process and the kernel. And we have such a queue pair for every core. And what we do is we put those requests in that queue. And we poll, the scheduler polls the return queue, and the kernel just executes those requests asynchronously. It sounds easy and nice, but there are actually a lot of limitations with the API. You have to bypass the page cache, and there are some restrictions. But this is an area of Linux that is continuously improving, in part due to our efforts, because it's a little bit esoteric, but it's really the best way to get not just high performance, but also predictable performance from your disks. All right, so CPU scheduling. In the same way that the disk is a limited resource that has a fixed throughput, the CPU is also such a limited resource. It can only execute 1 second worth of instructions per second, not more. So we face the same problems that you have different user queries that are represented by continuations running inside the core, and you also have internal continuations that are executed on behalf of the application without any connection to any user query. And we want those continuations not to overwhelm each other. So there may be several users that are using the system. We don't want one of them to send a huge number of queries and overwhelm the system, and the other users are just sitting and waiting for their queries to return. So what we do is we have the ability, in the same way that we do with I/O, we tag each continuation with some markers that identifies its origin, and it's inherited, so you don't really need to see it on every single continuation. You just set it on the top level. And you can assign shares to each scheduling group, and the scheduler will just do a round robin between those, a weighted round robin between those tasks, and this way you can control which user gets which share of the CPU. And of course, if some user doesn't need all of its share, then it gives it up, and other processes can gain from that. So, and what I mentioned before, that we give up some flexibility because we have only one thread per core, so we can't decide how many threads are doing which operation. This way we gain that flexibility back by not only running multiple continuations per core, but also classifying them into different scheduling groups. All right, coroutines. So if you noticed before that the syntax for doing sequential operation looks a little bit awkward, it's actually a lot more awkward when you have more complex computations. It quickly becomes harder to read. It's still much better than the callback style that you see in things like libev or libuv, but still it's a lot of boilerplate. And coroutines, which is a C++ 2a feature, give us the ability to write a lot more straightforward code. It also reduces the number of allocations. So before we had a question, doesn't each lambda need an allocation? And the answer was that often it does. So here we can have multiple bits of glue code between I/O that share a single coroutine, and so they can be allocated all at once. And this is translated transparently. So you write your coroutine, and the Seastar coroutine integration will translate it automatically into a continuation that can be scheduled by the scheduler. And so all of those different ways of instantiating task, either a lambda that is part of a then block, or a Seastar thread, or a coroutine, they can all cohabit in the same scheduler. And this is supported in an experimental mode already in Seastar. It's experimental because the standard for that has not been finalized yet. So as soon as C++ 20, or let's hope that it's not 21, is finalized, then we will declare it as a production feature. So what I described was the basic building blocks of Seastar, but there are actually a lot more. So there are primitives that allow you to combine continuations and do different things. There is an HTTP server and HTTP client, which are useful for controlling the system. There is similarly an RPC client and server that use direct C++ APIs. There is, of course, MapReduce and parallel for each. which allow you to run a function, multiple instances of a function, and you can also tell them to run on different cores if you want, and then collect the results. There are streams. They're the equivalent of C++ I/O streams, except that they are futurized. They're asynchronous. So when you issue a read, it will not return. It will return a future immediately, but the contents of that future might only be available when the I/O actually happens. I mentioned threads. There are some primitives that allow you to easily take an object and run it in parallel on all of the cores in your system. So that's useful for parallelizing an application. When all, it's actually a part of the C++ standard, and we have our own version that allows you to wait for multiple futures. I mentioned timers, and we saw sleep. There is a semaphore, which, unlike standard semaphores, does not use any locking operations and doesn't block. So it just translates the semantics of the semaphores that you know and love into continuations and futures and promises. And a bunch of things like that. Maybe an interesting thing is execution stage. So execution stage is an API that allows you to ask the scheduler to run multiple executions of a function close in time. And the reason for that is that modern processors have an instruction cache that has very limited capacity. So that by running a single function on multiple pieces of data, well, we will have the first execution. It will run a little bit slow because it is bringing in the code for that function into the instruction cache. But the second and third and later executions will run a lot faster. So that allows us to reuse the work that the CPU did in executing the first iteration and makes the following iterations much faster. So if you have a complex piece of code to execute, it gives you an easy way to execute those multiple iterations close in time, even though they come from completely different sources. We have TLS here. TLS is not thread local storage. It's a transport layer security, so SSL. Integration with Prometheus. So high concurrency application need a lot of metrics in order to make sense of them. Also DNS, because we run completely asynchronously. We need our own DNS implementation based on CRS, but again, translated into futures and promises. Yes?
Is there any definition of services? I mean, if you have different cores, and I guess you will want to assign different tasks for different cores, different services for different cores. For example, you may want the code near the network to handle all the network. So is there any registry so a process could know which process to ask?
Yes, a good question. So I think the question was whether there is support for asymmetric processing, where different cores have different roles. So this is not something we encourage. The problem with asymmetric processing is that you don't know in advance how much processing power an asymmetric core will need. So if you have a core for networking and a core for computations, if it turns out that the networking core is underloaded, then you have a core that is not doing a lot of work and a core that is overloaded and becomes a bottleneck. So what we encourage is make everything completely symmetric. Every core has exactly the same tasks, and let the scheduler balance out the different tasks. For some kind of for some applications, that's not the best choice. So some applications are really super latency sensitive, like the financial stuff, that the financial people that try to destroy the world by high frequency trading. So for them, it might make sense to dedicate cores. I hope there aren't any in the crowd. But what we encourage is make everything fully symmetric, and this way you can easily achieve full utilization of the system. All of the cores at 100%. It's something that people who run Scylla, the database that is based on Seastar, sometimes are worried that they have high CPU utilization. But I tell them that for us, if it's below 100%, then something is wrong. You should try to get the database fully utilized. It's good. It's working on your behalf. Yes, and it's two legitimate approaches. One approach is to have over-provisioning and put a lot of hardware on the problem and try to make the result as low latency as possible. And the other is to try to be economical and extract as much work as possible from each core and therefore deliver high throughput. And of course, it needs to be balanced. Even for us, it's not just about throughput. It's also about controlling latency, and that is why we have the schedulers, so that while we have some kind of background task that is chewing the CPU, we can interrupt it at any time and run high priority task and in front of it. Okay, ports, so of course support x86, but we also support the ARM and IBM-P, which is the IBM Power Systems, and Z, which is the mainframes. So it sounds like the mainframes are from the 60s, but they also run C++17 code that uses thread per core. It's actually pretty easy these days to write portable applications, because with C++11, a lot of the roadblocks towards portability are eliminated. It would have been a lot more difficult to do in C++98. So what features make Seastar possible? So the first of all is lambdas. Without lambdas, it would be a nightmare. For every continuation, you would need to declare a function. And then if you would want to read sequential code that is supposed to execute sequentially, you would actually have to read it out of order and keep referring to functions. So by using lambdas, things become a lot more readable and also more writable. It's easier to write things this way. And we actually can't use C++11. C++11 doesn't have enough features in lambdas. The features that we are missing is lambda initialization capture. C++11 lambdas have to copy the values. And in Seastar code, it is very, very common. It is overwhelmingly common to move the values from one continuation to another in order to avoid the copies. And so we need this feature, which only arrived in C++14. So if you're tied to C++11, no Seastar for you. Variadic templates, we also use them extensively. So the future class that I showed in only simple instances is actually variadic. And you can have a future that returns a set of items. Actually, I now regret that we did this, because this is better relegated to std tuple instead of having future deal with both of them, and it makes template metaprogramming more complicated. We also use const if. This is only in a small number of places because we try to be C++14 compatible, and that's a C++17 feature. So we only use it in a small number of places, and we often have to provide an alternative. Instead, we use metaprogramming usually. Coroutines, we provide that as an experimental feature. We make extensive use of the fact that you can customize allocation in C++. And that's not only for performance reasons, but it's also in order to provide control. So a Seastar application usually allocates all of the system's memory. So we not only take 100% of the CPU of the system, we also take 100% of the memory of the system. Then it divides it up internally. And the reason we do that is it allows us to have a callback when memory is exhausted, and a Seastar application can register a reclaimer. And this way, when the system starts to run out of memory, then the reclaimer is called, and it can start evicting internal caches. And this way, all of the memory in the system is fully utilized. It's either used for processing requests, or it is used for caching something. We don't have idle memory. So the system is always running in a nearly out of memory state. It is continuously recycling memory from its caches and using it for new requests. And this way, we maximize resource utilization. you also make sure of the new features that allows you to give operator delete its size, and that makes the deallocator much faster. Fold expressions, and so that's because we use the variadic template. So in some places, you can very succinctly perform a computation on a set of futures or on a set of elements of a future in a fold expression. That's pretty nice. We use concepts extensively. So because the input to functions like then and practically all of our APIs are functor objects, then it means that if you make even the slightest mistake, then the compiler will reward you with an error message that is like 18 pages long. And good luck deciphering that. So by now, I'm pretty good at doing that, but we don't want to inflict that on new users. So we attach a concept to all of the functions that accept a template parameter, a function parameter, and this way we perform validation that the call can be performed. So the parameter satisfies all of the requirements of the input, and when you get an error message, it's not deep in the internals of Seastar, but it's actually at the point of call. And that really helps new developers and also older developers when they make a mistake. But still, it's better not to make mistakes. All right, so some use cases. Where is a Seastar a good match if you're considering to use it? When you have a large amount of I/O, if you perform a lot of I/O, that's a good place. And databases and file systems are a great place for that. High concurrency, if you're running on a system with 20 cores, 30 cores, doing hundreds or thousands of tasks in parallels, for us, we can go even beyond. A mix of disk and network I/O. So I talked about composability before. That's one thing that Seastar does very, very well. So if you're doing replication, if you're doing storage, it's a great match. Complex loads, so simple things you can usually code with libuv or something like that and manage the complexity. But more complicated things, you need a framework that supports that way of thinking natively. And clustering is also a good match because in a cluster, you are already supposed to solve the problem of distributing work among the nodes. So distributing the work among the different cores is just an extension of that problem. So the examples are distributed databases. This is what we are doing. Object stores and file systems. So Ceph, the distributed file system project from Red Hat, is in the process of transitioning to Seastar. And complex proxies and caches, and there are a few examples. There is a Redis reimplementation in Seastar that does that. So for more information, some URLs, it's an open source project, Apache license, so you can go to GitHub. There is extensive documentation and a website that explains the architecture. And you're, of course, welcome to reach out. There's also a Slack channel that you can ask questions on and a mailing list. So please, if you're interested, keep in touch. Yes?
Yes, questions?
Do you need a special hardware to run, or you run on any x86 server?
Yeah, the question was, do you need special hardware? And it will run on your laptop, although it will eat all of your CPU. It will run on a 96-core server. It will run in the cloud. It will run on our machines, on a Raspberry Pi. It doesn't need anything special.
Yeah, in the cloud and with elastic, you can add every time new CPU because you're always running on the 100 CPU.
It will run on whatever number of CPUs you give it. So if you give it 1 core, it will run on 1 core. If you give it 90 cores, it will run on 90 cores.
I mean, Amazon gives you the possibility when you starvation, it adds more power to your...
Yeah, so don't let it. Of course, Amazon will increase the number of instances until you run out of money. Yes?
Can I integrate Seastar into my application, like part of my application?
okay, that's a great question. That's a great question. How to integrate Seastar into an existing application? And indeed, Seastar is very opinionated. It wants you to do things its own way, and if you don't, it will be very angry with you. So there actually is a mechanism to integrate applications and maybe do a transition to the Seastar way of things, or live forever in a partial way. And that was contributed by the Ceph team, and it's called Alien. So it allows you can tell Seastar to just use some of the cores and some of the memory, and leave the rest of the cores to the system. And there is a way to translate between the standard future and a Seastar future, so you can submit tasks to Seastar. It will work on them asynchronously on its own cores and on its own memory, and it will return an STD future for you, and then you can use it in the normal C++ ways. So yes, you can do this back and forth, and of course, Seastar threads can talk to the normal application threads, and that's very useful if you have a large application that you want to translate. I should actually add that to the standard deck, because it's pretty important for existing applications. Yes.
It's a Linux only framework, right?
Question was, is it Linux only? And it's Linux only until someone contributes Windows support. Yeah, so comment was that we rely on DPDK, but DPDK is actually an optional component, and you don't have to use it. If you don't use it, it will use the normal operating system TCP/IP stack, and it will run very happily, not with the same level of performance, but it will run. Maybe the Windows has its own ways of doing user space stacks. Maybe it doesn't, but in any case, that's not going to be the barrier.
Sometimes it's more efficient to perform network I/O on the CPU for the core is co-located with a NIC in the same circuit.
Yes.
So are you using it, or because earlier you said every core?
Yes. So again, a comment about symmetric versus asymmetric processing. So indeed, when often you have a core that is not a core, but a socket that is connected directly to a NIC, and that gives better performance. We can do that, but we don't, because we try to promote symmetric processing. So there are two ways to handle that. So if you have a multi-queue NIC with enough queues, then you can configure the system to assign a queue to each core, and this way the NIC will do the hard work of copying the data. So that's one way to do it. And the other is to dedicate a core or maybe two cores for networking, and do the rest of the distribution in software. And we use both modes depending on the hardware capabilities. So if you have a good hardware with lots of queues, then we will attach a queue to each core, and this way reduce contention. If you don't, then we will sacrifice the core or two in order to do networking. Yes. Yes. So the question was, what's the idle policy? What do we do when there's nothing to do? So Seastar spins for a short while. It's configurable, trying to look for more work, because going to sleep is expensive and waking up is hard. I know that from every morning of every day. So we try to spin for a bit. If there's work, great. We save the trouble of going to sleep and waking up. If not, we go to sleep. We inform all of the other cores that we went to sleep. There's actually a blog post on this topic, because going to sleep in a multi-core system is pretty hard. So go and look in our blog. It's one that I wrote about. It's pretty touchy, a pretty touchy topic. So we do go to sleep, and we tell all of the cores that if they want us to do something, they will have to wake us up first. So the system will not spin at 100% if there's nothing to do. It will go to sleep. What is that all the questions? Can't be. Thanks a lot.